All right, let's get started. So I have an exam 1 week from today at this time in this place. So you have an hour and 15 minutes, more or less. I'll try to show up 5 or so minutes early to give you a few minutes extra, but we can't really run late because I don't know people's schedule. So we can't start super early. We can't run super late. It's essentially going to cover induction or asynchronous machines and really only asynchronous motors. Mostly because we don't do a lot of stuff with induction generators. They are more common than they used to be because of the wind turbine designs that we've seen. But the reality of it is the vast majority of applications, I would be shocked unless you do a lot of alternative energy stuff or the future changes quite a bit where you would actually come across with an induction generator. So we really are focusing on the concepts of induction machines operating as motors. And remember the concept of an induction machine, right? Its rotor field is always induced, at least traditionally for this class, it's always induced from the stator windings. So whenever you have a current flow on the stator windings, you have the ability to induce a current into the rotor circuit. And that current flow in the rotor circuit is what creates the magnetic field that you need to rotate, because you always need two. You need one magnetic field to rotate, and then you got the other magnetic field, so they'll either will pull or repel depending on how the norths and the souths are lined up. All right, so we need two magnetic fields. We get one from the stator, and that second one, and this is why we call it induction machines, it is induced onto the rotor. But that does not mean that you actually always have to have that. And the case when you aren't going to have an induced magnetic field is when the speed of rotation of the rotor is such that it doesn't see the windings on the rotor themselves, don't see a changing magnetic field. Remember when we look back, way back, this is, a couple months ago, when we looked at a rotating magnetic field, and what do we determine? It's always 1.5 times the individual maximum magnetic field. It never changed. So the magnitude is 1.5 B sub m in the three-phase machine, and it never changes. So how do you get a changing magnetic field if the magnitude never changes? Well, that's because it's rotating along, and the physical windings on the rotor themselves are not spinning at the same speed. So because you have one spinning this way and one spinning slower, can't do, it's like walk and chew gum or whatever, can't do that. You'll have to help me out. But the concept is you can't get them to spin at the same speed. So because of that, you actually see it changing magnetic field. As you're rotating along faster, the winding that's gimping along is actually seeing that magnetic field change. So an induction motor cannot operate at synchronous speed. What is synchronous speed? It's what we determined a couple months ago. It's all based on the frequency and the number of poles, right? So your stator magnetic field has to operate at synchronous speed. Your rotor, the physical rotor, cannot operate at synchronous speed. Now, here's where we got to think about that a little bit, because remember, you're inducing a magnetic field, and the only way that you can induce a magnetic field is you get that changing, inducing a current, you have that changing magnetic field, which means that your current is going to be changing as well. Another way to say that it's a changing current is it's an alternating current, right? Kind of modifying a little bit, but because we actually change the direction of the magnetic field, we also induce an alternating current. And the frequency of that alternating current is going to be such that it is the difference in speed between that synchronous speed of the machine and the actual rotor rotation itself. So when you add that up, it's got a frequency, so it's an AC system with a frequency, that also has the ability to create a magnetic field. And that magnetic field is also going to rotate because it's originating from a three-phase set of currents that are on the rotor circuit. And so now you have a rotor spinning it along at whatever its mechanical speed is. And on top of that, you have a magnetic field that's spinning along at whatever the corresponding frequency is. And the combination of those two, the mechanical speed of rotation plus the rotation of the rotor field, the sum of those two is equal to synchronous speed. Is that a good thing or a bad thing? hopefully think it's a good thing because we want constant torque out of our machine. If we had them operating at different speeds, sometimes there'd be a lot of torque output, sometimes there would be no torque output. And what that would result in is a machine that would have very choppy operation. So that's why in the last homework, I asked those questions. What is the speed of the stator magnetic field with respect to the rotor magnetic field? What is the speed of the stator magnetic field with respect to the stator? What is the speed of the rotor with respect to the stator? Or the rotor magnetic field, and on and on and on and on. And what you're trying to do is really understand the concept of, or the theory of operation of how an induction machine operates. Okay, that's kind of the high level discussion. The specifics are all based on using that idea that you're going to have a difference in speed. So we have a slip speed, and the slip speed is the difference in synchronous speed and mechanical speed. Not typically useful, because why do I really care that the slip speed is 27 RPM when the machine operates at 973 RPM? That's not so useful for me. So what's far more useful is to know what the slip is. That is a percentage. So I can calculate what the mechanical speed is, and I can also calculate what the slip is. So this equation, this wasn't derived, this was just presented. We're going to define slip as the difference in slip speed, or the slip speed, relative to the synchronous speed. So it's going to be a ratio. It's a unitless quantity. And once we have that slip, now we have a proportion or a way of indicating how fast or how slow that rotor is rotating relative to that synchronous field that's rotating along, which is going to allow us to calculate the electrical frequency on the rotor. Right? We already said that that speed, that frequency on that rotor has to make up the speed difference between the actual rotor speed and the synchronous field speed. So now we can just calculate the frequency with that. And it's always going to vary between 0 and 60. Can't technically be 0, right? Because if there's no slip, then it means it's operating at sync speed. So, and we just talked about that can't happen. But it could go all the way to 1. And when it's at 1 is when we're under locked or blocked rotor conditions. The rotor itself is not moving at all. So now you're generating massive amounts of current, and your frequency of your electrical source on the rotor is, in fact, 60 hertz. And so then we use that concept of slip and mechanical speed or synchronous speed, and we could build a torque versus speed characteristic. So we presented the torque versus speed characteristic, you remember, sort of at the beginning of the chapter, because we were trying to understand the operation. We saw how under a typical NEMA design B characteristic, we had a pretty good amount of starting torque, or a locked rotor torque. And then it went up and up and up until it peaked at the breakdown torque, which is its maximum value. And then it drops off very quickly until we get to synchronous speed. So we could see the torque characteristics, and we could go ahead and do that. We then later learned how we can monkey with some of the resistance in the circuit to actually change how that curve looks. And we'll talk about that in a little bit. But why do we have this torque versus speed characteristic? It's really helpful to help us understand, you know, what's happening in terms of the torque output, but also if you do want to use this for regenerative braking. So another way to say regenerative braking is using it as a generator, right? Because anytime you convert mechanical energy to electrical energy, that's what we call a generator. So you could actually see as your synchronous speed is exceeded, so you're going faster than synchronous speed, you're now going and operating as a generator. And so how do you get it to operate faster than synchronous speed? Maybe you get things rotating in the reverse direction. You actually get magnetic fields going opposite. And so now you start to say, well, that actually causes things to look relatively different in speed. So a lot of times with regenerative braking, if you can control the power electronics, you can actually ramp the frequency down pretty quickly. Sometimes if you want to go really quick braking, you can put it in the opposite direction. Let's see. So we talked about operating the machine. So full load operation is typically only at very low values of slip. You can't run a motor for very long at locked rotor conditions, or even pull out or max torque conditions. It's just not going to survive. It's only designed to reject the heat. And that's when we rate a motor, 100 horsepower motor, it's always rated on what it can output continuously under normal conditions. So 100 horsepower motor, that's what it can put, and it only can do that at very close to synchronous speed. You can overload the motor. You can certainly try running it at 110, 120 RPM because the torque versus speed characteristic, or 120%, because the torque versus speed characteristic will permit it up to sometimes 500% of the full torque. It's just that you're pulling in so much current at that time that the motor is unlikely to last very long. Okay. So yes, you can operate it, but it's not going to last a very long period of time unless you're running it in more ideal conditions than expected. So normally motors are designed to operate in a 40 degrees C environment, which I think is like 93, 94 degrees Fahrenheit, which seems pretty hot for you and I. But if you're in an industrial facility and you've got a motor that's rejecting a lot of heat to the environment, that actually isn't that hot. But if you have a way of cooling the motor down, you know, putting it in an environment that's cooler, or having some sort of air circulation in that area, you can actually pull some heat away, and you might be able to push it for a little bit longer period of time. A long time ago, I was working at a facility, you know, I was on loan, I was helping somebody out, and it was the world's largest turkey processing facility. And they were wondering why their electrical equipment kept failing. And you walked in their electrical room and it was 110 degrees. And I said, did you ever think about putting an air conditioning unit in here? Because electrical equipment is not designed to live very long in these type of temperatures. And they got some, you know, somebody decided to open up the doors on each end, and they did that for a month or two and never had any electrical problems. And I hope that wasn't their long-term fix. I hope they actually ended up putting some sort of legitimate one. But yeah, a lot of times you just keep it cooler. So if you can run things at cooler temperature, that usually helps. One of the biggest things that people don't realize, if you ever work in an industrial facility, is cleanliness. Anybody here have a refrigerator? How do you make sure it runs at optimal efficiency and lasts a long period of time? There's fins on the bottom, usually on the bottom of your refrigerator. If you just vacuum those out every once in a while, your refrigerators run a lot and last a lot longer because they do a much better job of rejecting heat. So same thing with the motor. You clean the fins. And if you look, if you have an open enclosure motor, like some of the ones we have are open enclosure, but we have a pretty clean lab environment, right? You can look inside, in a lot of cases, you can see a tremendous amount of dust and debris that's in there. So every once in a while, just take a vacuum cleaner, or sometimes even better, take a compressor and try to blow the air out to keep it, blow the dust out to keep it a little bit cool. Because again, these things are designed to run for 40 years continuously. Even a 1% increase in efficiency can save you hundreds of thousands of dollars over the life of the motor. We are electrical engineers. We love electrical engineering, which means we love to analyze electric circuits. I don't want to analyze a hunk of metal with windings that's rotating and doing this and that. So you've been doing this all your career. You just may not have realized it, but the very first thing we do to be able to analyze a circuit that has electric motors in it, if we have to do detailed analysis, is build an equivalent circuit model. And here's our equivalent circuit model, which is exactly the same as the transformer equivalent circuit model, except we short-circuited the secondary. And that's why we talk about electric motors, basically a rotating transformer. All the concepts for a transformer are applicable to motors. The difference is that because we're rotating on that secondary side, that changing magnetic field is relative to something that's rotating, not stationary. So you don't get 60 hertz. You get different frequencies. But when you convert power, you get power out in terms of torque. You do have some I²R losses in your machine, but most of the power that we're really interested in is determined as based on that R2 value over S. So that again is a huge change in terms of the transformer equivalent circuit model. Is if you look over here, we have a resistor that is its value is dependent on slip, not the actual R2 value itself, but the overall effect on the circuit is determined by this R2 over S. So at really low values of slip, I'm almost at synchronous speed. So I'm hardly putting out any mechanical power. So that means this resistor better be pretty darn high to make sure I don't put out a lot of power. Under locked rotor conditions, I want this to be as low as possible, not because I'm putting a lot of power out, right? Because technically, if I'm not rotating, I'm not technically putting any power out, but I want to be able to put out massive amounts of power. And then again, you can say, well, wait a minute, Paul, if this is low, why isn't this putting one, which is the highest value you can get? Why isn't this putting out massive amount of power? Because maximum power transfer does not indicate that max power transfer occurs at the lowest resistor value. Max power transfer occurs when your magnitude of your source impedance equals the magnitude of your load impedance, right? So that's a very different discussion about, when max power occurs. And then you can just analyze the circuit. You just analyze the circuit with whatever circuit techniques you want. You can do Thevenin, which is one of the approaches we covered in this class. I also like to write loop equations. I know at one point somebody said do node equations, which is fine, but I got 2 loops and I've got, I don't know, 7 or 8 different nodes that I have to calculate all the voltages for. So it usually is more efficient in this particular case to calculate loop curves. Now, we usually, if we want to get really precise, we might want to break out R2 over S into 2 separate components. One of those components is R2, which is the actual rotor resistance. That's the heat loss that we're getting because of current flow in the rotor. And then the other term, the R2 times 1 minus S over S, is equivalent to what the actual P out is of the machine. That's equivalent to the mechanical power. Not the actual mechanical power that's available on the shaft. It's the actual mechanical power that is used to rotate the turbine. Because remember, we have friction and windage losses, bearing losses. We have a bunch of different things that we need to consider. So we need to take those into account. So dividing this R2 over S into 2 resistors sometimes reveals more information about what we're trying to do. Keep in mind that it's easier to write your equations with just a single R2 over S, but breaking it down gives you more useful information. I didn't copy the V Thevenin stuff. You're welcome to include that. I just did it if I was to do this by hand. I just like working with matrices because I get all the information I need, and I can do that here. So I included the matrices for solving for my stator and my rotor. I even modified those equations from I1 to I2 to say I stator and I rotor. And then I also included voltages here. I put V phase and I put 0, and I put the 0 in here because there is no voltage source on this secondary or the SI rotor side of the circuit. So once you do this, this is a pretty easy thing to introduce. As long as your calculator can handle matrices with complex numbers. That's hit or miss. I don't know which I know the TI-89s can. 84s can't. As I say, maybe 83, 84 can't, but the Inspire, I believe, can do matrices. I don't know. Can you still buy the 83 and the 84 new? Is it still for sale? Yes? The TI-84, you can buy it brand new? I thought they stopped making it because the TI-89 has been around for 15 years or something like that. TI-89 is going to cost you what? $10 now? $20 new?
EET4 is probably the most popular one.
It's the most popular one? Okay.
Yeah. That's what I'm getting, right? The new TI on the old one.
So the new TI-84 can do complex math?
Yeah.
TI-84C.
Yeah. C.
Oh, okay. Oh, CE.
Yeah, that's just a color edition.
That's a colored edition?
Yeah, like its display is.
Oh, that's what the CE stands for. So maybe the newer TI-84s can, I don't know. But that's why I gave you an option. If you do it with MATLAB, MATLAB laughs at complex numbers. No problem. You decide. I just like doing things and making it easy and going that way. I also gave you examples to look for relevant examples. You're welcome to take a look at that or not. It's totally up to you. This is another really useful one, which talks about how power flow happens in a machine. And I'm only including the motor one, not the generator one. Because again, we don't have many applications of generator ones. But motor, you take electrical power. And I'm being very consistent this entire semester. I know it's been like, fighting and pulling hair and getting it through, but we've always been consistent. It's a 3-phase power. So look at the equations. VT, which is typically a line voltage, IL, which is a line current, times the cosine of theta And don't forget, it's the square root of 3 there, right? Because this is a 3-phase machine. We don't analyze induction machines that are single phase or 2-phase. We only analyze them as 3-phase because I don't actually know of any single phase. They might call them capacitor start motors where they're single phase, but those are like, driving fans on a refrigerator. So if it lasts 5 years, you're happy. It's nothing that's designed for 40 years. So now we're all in the electrical world. So all our losses have to get taken away, are electrical losses, right? Because the electrons are flowing through something that has resistance, and that resistance is trying to prevent those electrons from flowing. So you have to overcome that, which means you have to consume power. So we have some stator copper losses, I squared R. Next loss is any core losses, and those are very difficult to obtain. So if you look at all the examples, I don't think we've ever given an example with an R sub C. But if you do have it, it's not a big deal to add. You can just do I squared R. Now we have converted power from the stator to the rotor, or we have transferred power from the stator to the rotor. So we've just gone across the air gap and are into the rotor. We're still electrical power. We're not torque at this point. We're still electrical power. So at this point here, we jump through the air gap. We call that air gap power. Now we're electrical, and we still have some work to do to be able to do some mechanical work. So we have to take out some rotor copper losses, those I squared R2 losses. And once we've done that, there's no other electrical circuits to deal with. Now we can actually take all the power that's left, and we can convert that to mechanical power to do something useful. Right? That's why there's so many more mechanical engineers than electrical engineers, because they just think, hey, mechanical engineers do something useful, right? You can actually see force and all that stuff. But we electrical engineers, we're like the bus drivers, right? We make sure that all those electrons get to the right point as fast, as efficiently as possible. But the mechanical engineers is who cares? We'll get there when we get there. So now we're power that's mechanical. We've been converted. So at this point, we actually have an equivalent output power, which is a torque. And that's going to be equal to our induced torque, not our output torque, but our induced torque times speed of operation. Speed of operation is going to be impacted by friction windage losses, so we got to take that out. We subtract that. And if we have any other losses that we don't know how to categorize, we'll just lump them all together as miscellaneous losses, take that final one out, and now we actually have shaft power, actually on the shaft, to do real work. Everything has been accounted for in the motor. That doesn't mean to say that the mechanical system is 100% efficient. They've got their own issues to deal with, but just from a electrical to mechanical efficiency, this is what we're going to do. There are way more mechanical losses in their system otherwise, but we have to get into more detail in mechanical systems to assess those. So a few equations in here. You can use whatever equations you want. I always find this to be pretty useful. The only thing I would say is the converted power was 1 minus S times the air gap power. So sometimes that's not always so obvious, but you can use that equation if necessary. And then you have your power losses here. And the reason why we do this, right, is because we take a look and we can look at this little flow chart and see where our power is going. We have 1 unit of input power. I just say it's 1. So it's a unit of power. It could be 100 horsepower. It could be 1,000,000 horsepower. It doesn't matter. It's 1 equivalent unit. And all the power that jumps across the air gap that actually gets converted to being able to do mechanical power, not output power, but mechanical power, is the ratio of that is just 1 minus S. So whatever your slip value is, you take that away, and then that becomes mechanical power. The S part of that is what's lost in rotor copper losses. So running that at very low values of S, almost 0, means we're not wasting any energy with rotor copper losses. All right. There's nothing we really can do as electrical engineers to get more mechanical power out. That's up to the manufacturer of the bearings, right? So every motor is going to have bearings on it, and you can spend a lot more money to get premium bearings that are really fancy. And anybody know how you make premium bearings versus typical bearings? You can use, the obvious one is use higher quality grease. What's the less obvious one? You have a bearing, right? Isn't that a piece of metal? So you have a bearing that might not be, that has some resistance with it. Why does it have resistance? Because it's not perfectly smooth. Did you ever look at a ball bearing in a car or a wheel, a bearing, or you ever take one out and put it in your hand? What did you notice about it? It's shiny, isn't it? It is perfectly shiny and it got a high, it has a high gloss. That's because it's polished to a very high level. That's where the shine comes from. They don't actually put paint on it. It's just a piece of metal and it's very highly polished. And that's why it has, almost a mirror-like appearance, because the smoother the surface is, the better the resistance. And even though it's shiny, it's still, if you could look at it under a microscope, it still has some resistance. And so what you do is you polish it at ever finer and finer grits. They roll them in a tumbler and you just continue to polish them with ever increasing grit. So you might start out with something that's equivalent to like a 10,000 grit and maybe move up to 100,000 grit, which is, if you're really looking at it, if you take, you can go and you can actually buy different grades of steel wool. Like some people like to polish things with steel wool. So you can actually get super refined steel wool so that it's almost like I said, a mirror finish. And that's how you can do mechanical systems. So that's pretty much it for that. And then this little discussion over here is about torque and power. You can use Thevenin's theorem, right? So figure out Thevenin equivalence and use that for max power transfer, which you can do the calculations by hand. You don't have to do any of these calculations here, ST max and T max, if you don't want to. You also don't have to do this T induced torque, because if we have a way of calculating the rotor current, then all we do is I2, or the magnitude of I2 squared times R2 times 1 minus S over S. That gives us the T induced. If you don't want to do that, you're welcome to use this equation here. So you get to decide. All right. We know our torque max, we have to have max power transfer. So we figure out when that occurs, and we can see that R2 is having a pretty big impact on ST max, where that maximum torque slip's going to occur. So this is what proves to us, if we monkey with R2, we put more or less rotor resistance, we can actually change the speed where our max power, our max torque occurs. Interestingly enough, R2 doesn't show up in this equation for torque. So that's an advantage of monkeying with R2, because you really can still get the same level of output torque that you want without having really to change the motor. That doesn't mean you're going to be as efficient. You're going to pay a penalty in efficiency, but you can monkey with that. This also might help you understand a little bit about, and I think Jude talks about it, if you've taken the PLC class, Jude talks about it, I believe, in her drives course, and I think ECE, they have a drives course now. But why do you use variable frequency drives instead of changing the rotor resistance? Seems like a no-brainer, right? To just adjust some resistors to get the speed characteristics. Really cheap. Way cheaper than buying a VFD. But now you got I²R losses and an external resistor. And you need brushes and slip rings to be able to get that rotor resistance into the circuit. So you tremendously increase the rotor copper losses, more heat generated. You got bearings. It's just more expensive to do it. So what do? You just buy a variable frequency drive, and it just changes the synchronous speed. How does it change it? It changes FE, that electrical frequency. So instead of 60 hertz, maybe it's 57 hertz or 55 hertz. And then that torque versus speed characteristic changes because the mechanical load demands a certain amount of torque at a speed. Well, if you move your synchronous speed, your torque versus speed characteristic back, then essentially what you've done is you're running it at lower speeds to get that same value of torque. So that's one of the ways that you can do it with variable frequency drives. So it's up to you how you want to do this, but you can do the calculations. And that's what these NEMA design folks do. Depending on the characteristics you want, they just build in, instead of adding a resistor, they just change the wiring configurations on there. So they might use less turns, they might use more turns. They might use a larger diameter wire to get the different classifications, the NEMA design categories. The most common one by far is B. You can find the other ones, but B is most common by far. Yes, sir.
One of the questions, are we going to be moving with NEMA
If you're not, then just assume B. Okay. So that's when I talk about the loop equations. And then how do we get all these parameters? We saw in lab that we could actually run these motors under different applications, and we didn't quite follow the rules for doing the block rotor test, but we're actually able to do DC tests to get our our stator resistance. Then we did the no load, or the basically the I'm going to say it's equivalent to the open circuit test. And when we run the no load test, right, we're getting very little values of slip. So we can get that value of R1 plus, X1 plus XM. And then we do the blocked rotor test where XM is too big. We don't worry about it. So we get X1 plus X2. When we do the blocked rotor test, we want to run it at lower frequencies, because running that thing at 60 hertz is really putting the motor under pretty serious strain. If you remember from the lab, you saw it spinning really slowly. If you were physically in the lab, you could hear the motor not sounding like it was enjoying life. It was sounding like it was pretty upset. But that's the type of testing you do. So if you run it at 15 hertz, 20 hertz, whatever frequency you want, it doesn't have to work as hard, because it's not trying to catch up as much, so it doesn't put out as much torque. But you get a pretty good result for your torques here, and then you just have to adjust, not torques, your impedances. So then you just have to adjust based on the frequency. And this table is just a standard table of how you can ratio X1 and X2. So from that block rotor test, you just figure out what design, and then you ratio from there. And then we saw this in lab, right? When we started an induction motor, sometimes we had the switch open, sometimes we had it closed. It didn't like starting when the switch was in the closed position, because it wants to instantly go to 1800 RPM. But when we had the switch in the closed position, because those damper windings, you actually could start the machine and get it to operate like an induction motor. Induction motor. I'm jumping around. I'm on a synchronous machine. I'm confusing you. Sorry. So this is talking about starting a motor, and we didn't talk too much about this in lab. But when we start an induction motor, the easiest way to do it is to crank the voltage down. Remember when we were turning up the voltage in lab, you'd see it start to spin up. So that's a way to do it. So you can reduce the voltage. That's how we've traditionally done it. You have these things called reduced voltage or auto transformer starters. Now, more in line, you actually will buy variable frequency drives, and then those can start synchronous speed at 1 hertz, 2 hertz, all the way up to synchronous speed. So in starting an induction motor, and the reason why you need to do that is when you start an induction motor, you're pulling a lot of current. If you remember from the lab, at low values of slip, we had excessively high values of current. And depending on how the system is set up, like every system in the world is set up to handle the full load conditions without any problems. Once you start running under overload conditions, all bets are off. When you start an induction motor, it's not unheard of to have 6 or 7 times the full load amps to do that. So that can cause problems with your system. And 3 little simple questions with 35 parts each. Kind of like the homework. Why do we do it like the homework, the test? Because it kind of hopefully leads you boom, 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 boom. You just kind of walk through the path. And there's a lot of different pieces of information. So if I give you a motor with some nameplate data, determine some of the operating parameters, output speed, output torque, mechanical speed. I don't think you could calculate current with some nameplate data. The next one is if I've given you current and some losses, determine power flow. So using that chart. And then the last one is if I give you the equivalent circuit parameters, you should be able to tell me the whole kit and caboodle of how that machine operates. Just like the homework. And that's it. You get an 8.5 by 11 sheet of paper. You can use your calculator. I was gonna say or MATLAB, but nobody in this class uses MATLAB, right? So you do?
Me too.
I prefer it.
You're switching to MATLAB now?
Yeah.
Really?
Yeah.
I thought you were gonna hold out forever.
Yeah. You went on.
You've given up?
My MATLAB is too hard.
Controls is done to
Yeah, controls art has done a lot to me. Last time, MATLAB control systems and then I'm like, "Ooh, something like that's really good.
Yeah, it's just like, it's the idea that the calculator is the hammer and MATLAB is the, the pneumatic hammer, right? You can put a lot of nails in, does them perfect every time. And as long as you know how to use it, and you don't shoot your eye out, you know what I mean? You're in pretty good shape.
You have a number pad.
What's that?
You have a number pad.
Oh, on your computer, yeah. Yeah, I'm not that skilled at that, so.
What are we gonna get for tables or anything? There's a few that were included in this, so those gonna be given.
I think the only thing you need is this one, right?
Are we gonna get that or is it?
I think you should copy this down. I wasn't planning on giving you any tables. This is the only one, right? Everything else
I
you should
guess it's like the
draw your equivalent circuit. We did it for transformers.
equivalent of.
Yeah, same thing, the power. I don't think, there's not that many tables here. There's not a lot of calculations that are new. If you remember at the beginning of the semester, let's see if we can do a call back at the beginning of the semester. This entire class is applied AC circuit analysis. That's all it is. We're introducing new equipment, but we're still doing AC circuit analysis. There's nothing different. So I'm not asking you, when we did Thevenin and whatever, is that something new? You got that in your DC circuits class whenever when. Or when we did loop equations. That's not new. That's nothing fancy. I squared R losses, again, go back to your circuits classes. Almost everything we do is based on using circuit analysis. What we're adding to it is how do you operate more useful and practical pieces of equipment. I'm sorry, electrical engineers, but a bunch of cabinets with some resistors, inductors, and capacitors is going to make for pretty useless life. Motors, doing real work, that can change the game for us. That's how we can, run our air conditioners or, I don't know, open up windows because we're too lazy to roll them down ourselves, right? Although ever since we've had power windows, it's completely freaked my wife out because she's convinced that we're going to end up in a body of water and she's not going to be able to get out. So we have one of those little pointy hammers that you can break the the side view mirror for the side windows.
And it's not as easy as it may.
No, because it's all treated with that plastic. I always told her just grab the seatbelt and hit it a couple times. Usually that's the same approach, but
Go for the corner.
corners are easier.
Pop the headrest.
What's that?
You pop the headrest off too. Yeah.
Through the headrest. Yeah, that's true. You just have to remember, you can't open the doors. So it's over. Well, if you don't break the windows or anything like that, supposedly if your car is a relatively new car, it doesn't fill up that quickly. I'm not saying you're having a party down there, but well, the problem is you've got some electrical shorts. I don't know how well the music's going to be coming in. So.
Ventilate that way. While you're on the ground.
That quickly. All right, before we get too out of control, all right, talk about dreary topics. Any questions?
We have to do that.
No. We do whatever you want. What's that?
We can do the loop.
But remember, I need to see your work. If results magically appear out of MATLAB, you don't get credit.
Like technology.
No.
They just like write out everything.
How do you do it for your calculator?
Yeah.
You just write it all out and then you just use your calculator to do the results.
Just take a screen, I'll send it to them.
No, it literally is just, it should be, for you all, it should be exactly the same as a calculator. You do all your work on paper and pencil to put your results in, or to show what you need to enter into MATLAB, and then you just use MATLAB to do the calculations.
But then now is doing that way is like I am limiting MATLAB. MATLAB can do more than that.
Yes, but this is not a test on MATLAB's capabilities, it's on yours. So I want to know, is the limiting factor you or MATLAB? And I doubt it'll be MATLAB. So that's why I don't allow people to bring scripts in and all that stuff, because you could bring a script in and just get lucky and put the right data in, and you get the answer, but that doesn't show any understanding. That just means you got lucky. And I'm not a fool to say people aren't going to have scripts. I mean, you technically shouldn't be bringing up any scripts, but I just know it's too tempting. But I'd rather see you do well. And if MATLAB is a more useful, powerful tool that you're more comfortable with, I'm willing to take the chance that, you know, there are some people who might take advantage of the system, but overall, my hope is that. And so that's why I keep you honest, which is you got to show me work.
Well, lucky for you, I still have no idea how to use.
It's lucky for me or lucky for you?
Yeah, I created the whole code before just put in everything and get everything behind us.
So you did a script. Yeah. But you know, the good thing about it, and you'll laugh about this, but Barzilli doesn't even realize it. By spending that time doing MATLAB and writing all it is, that's helping him learn.
Yeah.
So he actually outsmarted himself, which means maybe that's exactly what I wanted him to do. Reverse psychology. I'm not that deep. I'm not that evil. But it's like if you have this tool, everybody's comfortable with a calculator. Spend a little bit of time with MATLAB. You can call it with variables. And for me, it makes a lot more sense. And while I'm typing this in and learning how to use this, oh yeah, that does need to be I times Z. And it needs to be magnitude of I squared times R. So that hopefully, you know, reinforces some concepts.
Really get to use that. I don't know what calculate batteries, calculator.
Is that a hard task for you?
No. I don't want.
Fair enough.
Could you go back to the specific test questions? And is there anything that we have to use the test for?
No. Not on the questions I'm asking. I thought about putting a test question on there, but if you do transformer ones, it's more or less the same, so. Anything else? So when's the test?
Third.
Time? 11 to 12:15, right? I'll be here a couple minutes early. I'll bring everything. You just need to bring your calculator or your computer with MATLAB. Pencil, I'll bring scratch paper, and don't forget your 8.5 by 11. That's important. Work for neatness. Because at this point, as hopefully you see, it's, you know, I can give you more points if I can understand your work. There's 30 people taking this test, so I can't spend an hour per problem trying to figure out what you're doing. So I've got to see it fairly quickly, or else I'm not going to spend a lot of time giving you extra credit. But show your work and you can get credit. I do know you have to work diligently because you don't have as much time, but that is what it is. Anything else? Feel good? Feel bad? Are my tests too sneaky? Should be all the same stuff. Just building, right?
It's a lot of exams. Days.
So it's not me. Because we had our IAC meeting and everybody was saying that there's a big transition from John Allen's classes to my classes. Well, but I'm not, you know, it's not poking fun at me or John. It's just like, this is the theory. I mean, we're just applying that stuff. So it's, I don't know, I don't intend to go that much faster. I just feel like we're doing more practice with AC circuits.
Makes you feel like an upper class.
Does it?
Yeah, it's like, all right, we're in it.
Well, a lot of the stuff you got to be able to work in industry, right? So that's the hope, is you're learning not necessarily how to be an expert at AC circuit analysis, but some of the critical thinking things. How many times have we done power triangle? And how many times have I gone back to Eli, the ice? That's a practical thing, so that when you are posed with a question perhaps like that in industry, oh, it's leading like, I remember when Paul talked about phasors and just, he kind of made it all stick together. I can just give you, 500 problems, and I'm not saying this is what John does, but people I know in the past have said, okay, we're just gonna do problem after problem after problem after problem, and then you'll get the material. Do you really get the material, or do you really get the mechanics of how to do a problem? But then when you're out in industry and it doesn't look exactly like the problems you did time after time after time, now what? You're gonna be able to solve the problem? So that's why we try to do, at least in my classes, I try to do a lot of real world examples. Remember the transformer test? When I gave you all, what was it, 10 points on that first exam? That was that was stuff that we learned in class, but I gave you data sheets. And so you can see how you can apply those. Because in the real world, we're way more interested in how do you apply this material as opposed to, okay, do a nodal analysis for the 732nd time. So again, not putting down anybody. I'm not saying I'm better than anybody. That's just my personal thoughts. So I don't intend to make people feel, like it's too hard of a transition, but this is what I think you need to be successful is how do you need to learn this material. Anything else? Oh, you said you feel okay. We'll see you after Thursday. We need to show up with, it's almost 4:20, right? With a pack, have somebody outside with the 4:20 stuff or
I think they come off really bad.
monsters and caffeine. That stuff is probably just as bad for you in the long run, so.
Yeah, that sounds.
Well, I shouldn't say, I don't know. If 4:20 stuff is bad for you, it's, yeah, I don't know. I shouldn't judge. I don't do any of that stuff, so. I don't even drink alcohol, and it's just because I'm old and drinking alcohol isn't easy on your body when you're 52 as when you're 22, so.
Not coffee?
No coffee.
Really?
I just drink water, all I drink. No juice, no tea, no soda. No beer.
I don't know how you do it.
You get used to it. The only reason why you drink coffee now is because you're used to it, right? When you first had that cup of coffee, you were flying, but now your body has acclimated, so it's no big deal. Takes a little bit of time to get used to it, but
Get done.
what's that?
I have a lot to get done.
So don't I, but just drink water.
Oh, plus the.
All right, well, if there's nothing else, have a great day, and I'll see you on Tuesday. Take care, or Thursday. Take care, everyone.
I-